Hi, year 8. This is your lesson on Hooke's law. So to start off, we've got 3 questions. A ball something when a force is placed upon it. Number 2, where is DNA found in an animal cell? And 3, how does heat travel in gases? Pause the video now to answer those questions and we'll go through. Okay, so if you want a purple pen, your answers. A ball deforms when a force is placed upon it. You would have done that in your last lesson on squashing and stretching. Number 2, DNA is found in the nucleus of an animal cell. And 3, heat travels by a process of convection. So hot particles in the gas rise, and as they cool down, they begin to drop towards the floor. Okay, so a quick recap, because we mentioned this at the end of the last lesson. The extension of an elastic object such as a spring is described by Hooke's law. And this is an important bit to copy down. The extension of a spring is directly proportional to the force applied to it. So directly proportional means that whatever amount the force increases by, that's the amount the extension will be. So if a spring was carrying a load that made it stretch 1 centimeter and then the load was doubled in mass, the spring would then be stretched 2 centimeters. So it's directly proportional. You're going to investigate the weight on a spring. So this is what practical we would normally do if we were doing this in class. And we'll go through and look at how the practical is done and expected results towards the end of this lesson. Weight is a force and is therefore measured in newtons, so it's the force due to gravity pulling us towards the centre of the Earth. So on Earth, if you have 60 kilos mass, you are 600 newtons of weight. 1 kilo is 10 newtons. So this is the practical that we would do. So we would have a clamp and clamp stand holding a spring, and attached to the spring we would have masses. We would obviously begin with only one mass and then build it up, and that would be our independent variable, the amount of mass that we change. Our dependent variable, what we measure, is with the ruler, so it's the extension of the spring, how long the spring gets. Now you would expect, obviously, as you add more weight, the spring will extend and become longer. But it's important how much it extends. So this is the type of table that we might get and the type of results that we might get. So we've measured here, we've started with our control with 0 grams, the spring was 20 millimeters, 10 grams is 25 millimeters, 20, 30 millimeters, and so on up to 50 grams. And from that data, we've worked out the first extension. So for 10 grams, we worked out that the extension is 5 millimeters. It's increased by 5 millimeters. The other rows in here are currently blank. I'd like you to pause the video now and find those missing numbers. So to work out the extension, the formula is in the box on the right there. Extension is equal to the spring length, which in the case of the 10 gram mass, is 25, take away the original length, which is 20. So all of them, the original length will be 20 millimeters. That's how long it was to start off with. So pause the video now to calculate the extension for the remaining 4 results. Okay, if you've managed that, then you should have these numbers. So going up 10, 15, 20, 26. So hopefully from that we can begin to see a pattern. Now, it is not uncommon for our results to have a slight margin of error, and I'm sure we can assume, based on the fact that it is a human measurement, that there could be some human error involved, as well as anything with the equipment that we're using. But let's continue and have a look at what we might expect our graph to look like from this. Okay, so you're going to plot a variable, plot your graph. The dependent variable, that's what you measured. In our case, it's the extension. We're going up the y-axis. The independent variable, what we changed, which is the mass, going across the x-axis. Okay, make sure, remember, for your graph, you have an appropriate scale. You plot your points carefully on your graph and then draw a line of best fit. circle any anomalies that don't include them on your line. Okay, so your line of best fit does not need to go through all of the points, and if there are any that stick out as being anomalous results, then just put a circle around them. For an extension, you can use your line of best fit to predict the extension of the spring with different size masses to that you used. Okay, you pause the video now. You'll need some time to draw that graph accurately. Okay, so your graph will look a little bit like this. You may have a different scale because obviously you didn't use the kilograms, so you have not used the numbers on here, but what should be very similar is your line of best fit. It should be a straight line of best fit going up because the two are directly proportional. So in this example, we've got the extension this time in centimeters because we're using larger masses. We're measuring in kilos rather than in grams. And we can see as one increases, so as it goes up in kilos, it's going up in the extension. So in terms of what this graph shows us, it shows us that extension and mass are directly proportional, and that is Hooke's law. You can see there, so 2 kilos is 4 centimeters, 4 kilos is 8, so both have doubled. 8 kilos is 16, again, both have doubled. Okay, so like we've just explained with the example graph, I want you to look at your own graph, your own data, and use it to write a conclusion for what has happened. Okay, use what you know about Hooke's law, about the extension and the relationship between the mass and the extension. Okay. So you have investigated Hooke's law. One of the statements below is Hooke's law. Decide which one it is. Okay, so hopefully you would have identified A as being the correct answer. As you double the force on a spring, the extension doubles. Okay. Last thing for this lesson, what does weight do to a spring? Describe the effect of weight on the spring. That's Hooke's law. Sketch a graph to represent the effect of weight on the spring. When we say sketch, it means we don't need to use graph paper. We can just draw using a ruler what the graph should look like. Explain the trend that it shows, and explain what happens to Hooke's law after the breaking point elastic limit. How is this effect seen on the graph? Okay, pause the video now to answer those questions. So here we can see the weight causes the spring to extend. As the force applied to the spring is doubled, the extension doubles. That's the sort of thing you might have drawn for your graph. And you can see we haven't got any numbers labeled on our axes. We've just got what it's showing us, so extension against force, and it'll be a straight line. The graph shows a linear trend, straight line. As force doubles, extension doubles. Hooke's law is no longer obeyed after the elastic limit. This line of best fit will become curved after this point. Okay.